Okay, our speaker today is Robin Young, who is a second-year PhD student at Cambridge, and he'll be talking about his recent work on calibrated probabilistic interpolation for GEDI biomass. Okay, or more broadly, interpolation using Tessera, I think is probably.
Yeah, interpolating any kind of sparse sample data on some spatial scale using good calibration.
Okay.
Good calibrated models. Yeah.
Go for it.
Yes, thanks, Keshav. So I don't think I need to convince people here that trees are pretty cool and we should care about them, but like this is here, we should care about trees. You see that like we've got a lot of trees going down over here, and we want to find out exactly how much trees are going down. And people put money on the stuff. They bet on like trees going down, or we plant trees to get money. So even if you don't care about trees themselves, people outside of that do care about making money. So how do we do this well? You could train a model, and NASA has a laser on the International Space Station that shoots down and then tells them how much tree is there. But the space station goes to and looks over the Earth in like specific tracks, and so the laser also has tracks like that. And besides the places where you have the actual measurements, there's a lot of places that you don't have, and even where you do have data, it's often very it's sampled in a very specific way, like you can see here that it's got the crisscrossing pattern. And this is what I mean by sparse data that is not IID. You're not having a random sample, and this messes with assumptions about machine learning. And interpolating this well is what I'll be talking about today. And usually in remote sensing, the default tool that people reach for is you use a Random Forest or use XGBoost. And if you put it in, if you put the GEDI data in, you have some covariates like road climb or elevation, you could get a pretty good model out of it. And it will even look pretty realistic. Like you look at the map, it looks good. And if you want to calculate uncertainty, usually people do report RMSE, and this is kind of a way to measure like how much things are varying across the area where you're testing. This is a measure of uncertainty or variance, but I will be spending the rest of this hour to convince you that you should not be doing this, or you should be doing way more than this. Because if you look at this, so on the left you have trees, they're pretty consistent. It's mostly trees. On the right, recall what we looked at earlier. You have a lot of trees, but then there's areas where it's very sparse, where they're cutting down trees right as they're taking these photos. But you could theoretically get the same RMSE from training a model on these two areas. And this, of course, validates our intuition on if the variance across these areas are the same. So RMSE is not a great metric for telling us what the local variance or local uncertainty at any given point is, because you're aggregating that to a single global metric and you're losing information over there.
Wait a minute, just repeat this point again, because the RMSE is for model prediction, right?
Yeah.
It's error in the prediction. Are you saying the prediction errors are both on the left, the same on the left and the right?
It's that I'm saying that it could be the same, right?
Yeah.
You could imagine a scenario where it's the same, but that would violate our strong intuitions on how much the local point where you're predicting, like how much the RMSE tells us about any given point on like either of those maps, right?
But you could calculate an error for every point from your test set.
Yes, and
then have some spatial distribution.
I'll discuss that.
Yeah.
Okay.
Yeah, so if you have a random forest, right, you could calculate the specific variance of the points that you're predicting by, you have 100 trees in a random forest, and each tree predicts some value. And the random forest model's mean output is the ensemble mean of that. So you could calculate the variance across all those trees, and then that would be some measure of how uncertain the model is about that point. But I will convince you, or try to convince you, that this is not a good measure of uncertainty. And this is mostly what people do, because Random Forest is a very popular model, and it's also very easy to use. You pip install scikit-learn, and then you go from there. It's very easy. And it's also a very natural way to think about uncertainty because you've got the model. The model already is an ensemble. You measure how much it varies across the ensemble for some point, and you get a very natural feel about, hey, that's a measure of uncertainty about this point that I care about. But we should really think about like what is the mathematical meaning of ensemble variance of the random forest? Is it telling us about, for this point, how much does it matter that the data that we're training it on has an effect on the stability of the model, or is it actually a good proxy for how much a point like that across some sample distribution that you're learning from will affect like what you're learning? If you're trying to learn some some distribution of points from the samples that you have, is it a good proxy of that, or like what is the mathematical meaning of ensemble variance in random forest? And so this is what I got to try to demonstrate the point that I was getting at earlier, because it's kind of abstract. But essentially, if you look at the left, this is what a random forest may be measuring. So say if you have some 100, 500 random forest trees, and then in the training set, you have this many data, right? And for the specific tree, any given tree, it will have some bootstrap sample of that training data. And you repeat this across all the trees. And what this is going to do is that each tree has some sample access to the training data. And this ensemble variance metric is essentially telling you how stable the model is with respect to your training data.
The choice of training data.
Yeah. And so if you look at the red box, this is the mathematical meaning of the ensemble variance, where you have this many trees, and the ensemble variance is how much they agree.
It might help you to stand there and point to the boxes, Robin, instead of sitting down just.
And there's people online.
Huh?
There's people online, right? So
Yeah, that's okay, but I mean, they chose to be online.
yeah. Yeah, so like if you take this is the training data. Each tree gets some subsample of it, and it learns and predicts some value. And so at testing time, the ensemble variance is for how many trees, how much do they agree? And realistically, depending on the test data landscape, it might not be a very good variance or uncertainty estimator because of how this mathematically works out. Because if the data largely agrees when you're doing the training, then it's not a good capture of how the testing data will actually vary on the landscape. Whereas, and this is the rest of my argument, that we do want to learn the predictive uncertainty. So for some spread of points, some sample of points, we want to learn how points like this point are distributed. And that is not conditioned on how the model is being trained. Like, it's not conditioned on the stability of the model. That's a different metric, which is over there on the left. And this is, say, like, if you look at the blue box over here at the top and at the bottom, those have a different spread of values that we're trying to learn from. And these have different variances in the data distribution. And so we want to learn, for some point, we want to learn a plausible distribution that it's sampled from, right? So above ground biomass is usually log normal. So for this example, we want to learn a log normal distribution for points, like any given test point that you want to have. Like you want to learn a function, a distribution function for where you could draw that. And if you have this distribution function, then you will have a good estimation of, hey, the mean is over here, and we learn the variance of it, and then we have a good idea of how points like these points may be distributed. And this is a good metric for uncertainty.
I think this is very important. Are there any questions about this? Because we really, this is
yeah, this is a very fine statistical point. But it's
have you considered like the aleatoric epistemic method, and how is that related to this phrase on this slide?
Yeah, so I will be getting into this a little bit later, but essentially a neural process learns both of those. And the aleatoric uncertainty is this component, basically. This is the deterministic path from attention, because you're gathering the spatial context from attention on your point that you're predicting from nearby points that you have as the context. And then epistemic uncertainty is what the model learns with the latent component globally.
I mean, sorry. Maybe I'm going to give you my simple-minded explanation of this as we discussed this a while. And the one on the left is something like this. Again, it's a very stupid idea, but let's say I have a dartboard and I'm going to throw darts at the center target, right? If all the darts hit the center, we'd say, oh, that's really good predictor because it's all hitting the bullseye. It could be the wrong dartboard. So you have two dartboards, A and B. Right? A is the one you want to hit, B is the one that's far away from it. And all your darts are hitting the bullseye of the wrong dartboard. That's what on the left is. So the model isn't varying. It's all saying, yes, I got bullseye each time. There's very little predictive uncertainty. It's all predicting the wrong thing, right? So that's what model stability means, right? So if all the weather forecasters say tomorrow is going to rain and they're all wrong, they all have high confidence, but they're all wrong. It doesn't matter they have confidence. And the problem is that what Random Forest changing the bootstrap and doing stuff is doing is simply checking to see how much they agree with each other rather than how much they agree with the ground truth. That's the problem. So the uncertainty is all in the training, as Robin said, rather than in the testing. And that's really like the wrong way to do it. And what predictive uncertainty, as Robin phrases it, is basically what's also called conditional variance or aleatoric uncertainty. Or what that's saying is, let's say I predict the above ground biomass to be 100, like what he shows over here. And in the ground truth, sometimes it's 90, sometimes it's 110, sometimes 104, sometimes 116. So I get a distribution of all the ground truths corresponding to a prediction of 100. And if I take that distribution, which is what is showing on the blue over there, and we compute the variance on that distribution. Now we say, if I say 100, I could be between 94 and 106 with probably 95% probability. That's my two sigma distribution. That's really what we want. But all the papers that at least Robin looked into are confusing the two things. They're trying to get the aleatoric uncertainty from the ensemble variance, which is like basically wrong. Mm-hmm. And so this is the fine point that he's trying to make, and unfortunately, understanding it there's too many terminological issues. So you see, the left side says wrong dartboard, the right side says just figure out what the ground truth was for a particular prediction. I think it's a very, very important part.
Yeah, I think a very important part in understanding is that if you have ensemble variance on a map. Like if you map this out, this is telling you how much does the model agree that that point should be that point. Yeah. And that doesn't tell us anything about like what is the distribution of points. Yeah. And another final point is that if you take a look at this is the bootstrapping method that Random Forest uses. And if you think about that, all the bootstrap samples are highly correlated to each other because usually they have like 67% bootstrapping of the training set. So even with that, this is not a really valid way of estimating the ensemble variance because all the samples are correlated.
Yeah.
Could you say that if you had like a random forest where every tree just says 100, outputs 100, then the ensemble variance of that would be zero.
Yeah.
Right. But that's not what does that even mean, right? Because
all the trees agree.
Yeah, exactly.
Clearly that highlights intuition on what you think the uncertainty of the point should be, right?
Right. And then just to follow, is the second thing, the predictive uncertainty, is that kind of model agnostic?
Yeah, you can model any distribution. Like you just have to specify the functional form of it so you could actually calculate it. I use a log normal, like I log the source data, so it roughly looks like a Gaussian, and I model a Gaussian because it's very easy. Realistically, for like probably student speed would be better, but that's really hard to get training stable and so on. Or there are ways to do non-parametric ones, but I haven't gotten to those. And yeah, so the buffer biomass and forestry data roughly looks log normal, as in it's exponential power law shaped, and so you take the log of it, roughly looks normal, but the tails would look different. But we could roughly assume that it's a Gaussian. And so here we could check the calibration of how your model is doing by comparing it against the hypothetical Gaussian distribution. And then you could check the calibration of it by calculating some stats on the residual of the prediction versus the ground truth. And this is the Z metric on residuals, and you can calculate the mean of the residuals and the standard deviation of the residuals. And there's also a couple other ways, like you check the coverage, like at 1 sigma, 1, 2, 3 sigma, it should cover 67%, 95%, 99.8%. And people should be checking this because, like, when you have a measure of uncertainty, you should actually calculate how calibrated it is. Otherwise, you're pretty much bullshitting people. Because you don't actually know whether that measure means anything at all.
So this is the aleatoric uncertainty. So you're basically quantifying, if you make a prediction, what is the variation in that prediction as a log normal? So you can say this is exactly how much biomass.
And so the method that I'll use here, I'll explain, this is a conceptual one. So many of you will know a variation autoencoder. It learns latent from some source sample data, and then it reconstructs something out of the other side. And you could kind of think of it as if you have a group of dogs, then you have a VAE at the middle. It will learn the latent of what a dog looks like. And then on the other side comes a dog. You can sample it a couple of times, you get a different dog. And then conceptually, if you think about it, I will explain neural process as this. You take a VAE and you go one level higher. So instead of learning a latent, you're learning a function of distributions, which the samples are drawn from. So in this case, if you have a sample of dogs, the neural process learns a function of distributions of which the distribution of functions which the dog samples are drawn from. So it's learning a latent space of functions, and you can sample this latent space. And each time you sample it, you get something like, oh, this is the function for golden retrievers. And then if you sample that function, you get one golden retriever. This is like the conceptual sketch. Basically, if you take a VAE and then you go one level higher, you're somewhere in the neighborhood of a neural process. And on the spatial scale, this is kind of what it looks like. So if you have some spread of spatial data, and this is, I guess, like a good demonstration of what spatial data actually looks like. And then you learn, you train a neural process on this. And then here you have this latent space, and what the space actually is, it's not the value of the point. It's a distribution of functions where a point of that value could be drawn from. And in inference time, what this could actually do is that because you have a function, like you have a function of distribution at that point, it will tell you what the mean is and what the variance is at that point. And what this has a very useful property because you can condition this on the points that you actually know about the truth of. So for example, this green point over here, there's a lot of red clustered sample points over here. So we know very well about what this landscape looks like. And it will predict a narrower distribution for the value of that point. And over here, it's further away from what we know about. So naturally, the model is less confident about it. And this is a very useful property. And because this matches our intuition about what spatial data looks like and how we should be learning about spatial data.
So each point maps not to a value, but to a function, to a distribution, actually.
Mm-hmm.
Which is the, I think I said that's a generalization that Robin is mentioning.
And practically,
this is not readable.
Yeah, okay, I'll just like describe it. So essentially why this matters is because if you're like, just look at this part. If you have a transition between a forest and cleared land, what we should care about is that if you have a point at the transition zone, then intuition will tell us that this should be kind of uncertain. We should be very uncertain as to what the true value of this point actually is, because the landscape looks very different on either side of that point. And this is the spatial context. And if you're using a random forest or an XGBoost, you're not capturing this like spatial effect, because the random forest will tell you that for any point that has the features that look like this, it should have the same value. Like if it's here, or like any other point on Earth that has this specific feature input, it's deterministic that it will output the same value. But that's not true, because we do care about what's around it. So the attention component is essentially grabbing all the nearby points as context and then conditioning the distribution that's predicting on that. And so this really helps getting the distribution right. And the summary of the argument is that we should really be thinking about like what uncertainty we should be measuring, as opposed to like, oh, is the model stable across the training sample data? Because yes, that's important, but that's not the semantic meaning of uncertainty that we actually care about if we're trying to map something. So more practically, I'll be talking about what the training data is. So you guys know Tessera. I grabbed Tessera. Then GEDI, I also grabbed GEDI, and a GEDI shot is a 25 diameter circle. And so I grabbed 3 by 3 Tessera embeddings, and that's a patch that roughly corresponds to a GEDI shot. You match that, and then across my study areas are 1 by 1 degree boxes, essentially across a couple different areas. And this is spatially blocked and buffered, so we don't really get spatial autocorrelation effects. And the normal 70, 15, 15 test train valve test slip. So that's all quite standard. And for example, this is what something in the study area might look like, and this is in Colombia. And this is an active deforestation frontier in the Colombian Amazons, and people cut down trees to plant coca so they can grow cocaine and sell that for money. And so it's a quite uncertain area as to what the true biomass is, because people are always cutting down trees and planting trees and so on. And then there's also a couple other points other sites in the Colombian Andes, and then a couple others in Europe. In Maine, in Europe, and in Japan as well. So I'll be going over those. And the comparison is, the baseline is random forest. This is a vanilla random forest, nothing special about it. And for the XGBoost, we strengthen the base case for this because it's learning 3 models actually. It's learning the mean, and then it's also learning 2 quantiles, and then we can use those 3 metrics to reconstruct a proxy for the distribution. So this is comparing against the neural process to see if the spatial context is useful, because this is also actually capturing the predictive uncertainty, but in a kind of a proxy way instead of a more principled.
That's elegant fashion.
Yeah, so here is the cool data table. And you can see that for LiDAR, which is the main area that I talked about, if you look at the log R squared, it performs mostly pretty well. All the models are competent. But where it matters is that if you look at the calibration over here, the calibration for AMP is essentially perfect on the residual. So the residual mean to be 0, as in you're not biased one way or the other on what the true value is. And the standard deviation on the residual is also measuring the variance of the distribution of residuals. And if you look at, for XGBoost, for example, 1.4 means that the XGBoost is 40% more confident than it has the right to be, because it's wrong. It's wrong on the distribution of residuals. And if you look at Random Forest, then it's really, really wrong. It's like 700% wrong on the residual variance, because essentially it doesn't know what the right metric of uncertainty that it's being tested against. Because the random forest was calculating the ensemble variance, and that's not the correct metric we're measuring against here. And if you look at the 1 to 3 sigma coverage, you could get a more intuitive idea of whether the predicted points actually fall into what the theory would tell you that it should fall into. And for AMP, it mostly does. And in fact, if you look at 1 sigma, is somewhat conservative. So this is kind of a good side effect for biomass, because if you're trying to do conservation or something like that, you'd rather be more conservative than too aggressive. If you look at those are mostly pretty aggressive. They're undercovering essentially. So what that tells you is that the predictive uncertainties of those models you should not be trusting them.
So I think the upper level tells us that all of them have pretty good explanation for the
Mean value.
For the mean value. So means are relatively, even random forest is very good. When random forest tells you that it's very confident, actually it's lying.
Yeah.
Because the actual Z score is way off from what it should be. So
yeah.
So it's confidently lying, basically.
Yeah. So the takeaway from the top is that if you want to get a good model for the mean estimate, then all of these are quite good. But if you do care about what the actual uncertainty is for any given point that you're trying to predict, then you should pay very close attention to what you're measuring and how you're learning from it.
Just clarification. So all of them are using Tessera plus the GEDI balance for the interpolation.
Yeah, all the data is the same.
All the data is the same. Sorry, go ahead, James.
I was going to ask, is this like cross-validation? I mean, the uncertainty on accuracy metrics. I'm not sure what could be. So how your accuracy metrics, how are you measuring the uncertainty on this?
So I don't have a diagram here, but essentially you have a 1 by 1 degree box, and I break that into 10 by 10. So each tile is 0.1 by 0.1 degree, and so there's 100 tiles, right? So I take 15 tiles as the test, and then 15 tiles as it's the normal 70, 15, 15. And so for test tiles, I look at all the neighbors and I chop those, and then I use train and test. I use the train and val to train the model, and then the test is the validation here. Then this is on test.
You would problem, so you get the uncertainty one.
Across 15 seats. Yeah. Anyone have questions?
I have a question. You were talking about spatial context for the neural processes. Where is it getting the spatial?
So it has an attention component that draws the context from the. So how a neural process training works is that for each sample, you can consider it as if you have a bag of points, and some points in those are context points, and some points in those are target points, and then you condition the model on the context points and try to learn what the targets are. And so,
but does it know anything about the spatial relationship between the points? So that is part of the input?
Yes.
lat long or?
Yeah, there's a normalized lat long, and all of them have access.
I see. Okay. Yeah. Okay. Yeah. Because I thought it was just the embeddings, and then I was like, wait, but they. Okay.
Yeah, I forgot about that.
You should put the neural process figure just so people that see what's going on there. Yeah.
Yeah, and I did hyperparameter sweep. So just to be fair to the baseline, saying essentially it's not very good. You can sweep it all you want, you're not getting a good model out of it. So the y-axis is how good the calibration is essentially, and the x-axis is the mean estimate log r squared. So if you look at the left, if you look at random forest, you could try to hyperparameter sweep it. You're not winning. It's approaching approximately good, but you're not getting there. And the points are bigger or smaller according to how long it takes to train. So when you're getting here, this point takes a couple hours. And for XGBoost, you're not even getting a consistent spread, because empirically I tested this, and the effect is that if you're tweaking the random forest, you consistently get better. But for XGBoost, you're essentially having to trade between how calibrated it is and how good the mean estimate is. So if you basically cripple the XGBoost, you have a really tiny model over here that's actually really calibrated, but it sucks. So like it's not very useful at all. And the AMP is just pretty good. So like trade-offs wise, even if all the models are pretty consistently competent at learning the mean estimate, those are not the same thing when you consider the Pareto frontier between the variance, the uncertainty versus the actual mean estimate performance. Yeah, and going into does it generalize? So I tested a couple of extra regions, and so that's main, and that's mostly just 10.4. It's not very exciting, but it does work. And then on subtyral, it also works. And more interestingly, in Hokkaido and Tolima. So Hokkaido is very snowy, and snow has interesting effects on embeddings, I would assume. And if you look at over here, so XGBoost was usually pretty competent, but over here, the XGBoost did not perform very well at all on Hokkaido. For some reason, I don't really have a good reason for why that is, but it's interesting to think about why, perhaps. But the AMP is almost always pretty consistent. And for Hokkaido as well, it was actually underconfident, as in like it really wanted to be conservative. So it must be something about the Hokkaido landscape itself that has an effect on the model metrics over here. And Tolima is the Andean part of Colombia, so it also has an interesting like biogeographical substrate to what generates the GEDI data, and it also performs pretty well. And just overall across those 5 sites, the conclusions hold that the AMP is at least as good, if not better, on mean estimate, and on calibration, it's pretty much always perfect, while the other models have varying degrees of how good they are. And so another point is, does it really generalize? And this is basically trying to torture the model. Essentially, this is transfer learning. If we train the model on one place and test it on another, does it do well? And the answer is no, it sucks, as you would expect, because the underlying distribution shift is too big. This might not be very easy to read, but essentially red is bad and green is good. And the top is AMP and the bottom is XGBoost. And it's pretty much always kind of bad. But if you look at the leftmost panel, that's the calibration part. And AMP consistently does better, even though it's always pretty bad on the mean estimate. But can we do something about this? Can we have good transfer learning? That's interesting, right? So yeah, this is another point. Why is it that the AMP does better even on calibration, even without a distribution? I'd argue it's because that the model learns to be uncertain as opposed to being conditioned on global metrics. Because the AMP has spatial context, then if you really evaluate it on somewhere else that has like 0 context, or it has context from really, really far away. So it learns to say like, I don't know anything about this. And when ask me, I'll just predict a very, very wide interval. And the XGBoost has no way to do this because it's essentially deterministic. And so how much can we recover the performance by doing 2-shot learning, for example? And so if you take the diagonal line, which is the train test on same region results from earlier with AMP, and then you give it a couple of test tiles, you give it a couple of extra tiles from the train of the new eval region to condition them on how much is to recover the performance. And one advantage to using a neural process is that it can receive gradient updates by retraining, like further training it along something else. Whereas you cannot really do this for random forest or XGBoost because trees are deterministic and you cannot like retroactively update the splits. If you add new data, you could add new trees, but it's averaging them across all trees are bad for that region. And what this does is that it works. You can recover most of the performance by having a little pre-trained model and then giving it a couple of sample tiles from the region that you're interested in, recovers 77% on average of the performance gap by having 10 sample draws from the new target region. And I think that's pretty amazing. And if you look at the metrics, it mostly does pretty well, and the log performance recovers greatly, and also does fine on the coverage and uncertainty metrics. And that's a usable model, even if not like ideal, but you're doing this with very little data, which I think is a very good property to have. And so this is some like statistical nerd stuff about looking at the calibration. This is the bottom right is a quantile plot. Essentially, it does very well between plus or minus 2 sigma, and for beyond that, it deviates from the hypothetical ideal. And probably this is because of a couple of things. One is that the training data is not perfectly Gaussian, so that it has a different tail behavior, and also that the tails have less data, so it's naturally harder to get it calibrated correctly. And then if you look at the top, this is the coverage and the hypothetical coverage that it should have across the board. And it actually does quite well. It pretty much coheres to the hypothetical that it should be getting, except for in the middle range where it's somewhat conservative. But this is probably a good thing that is not ideal statistically, but it's good for mapping.
Why is there a spike in the residue?
No idea. Probably just like.
I mean, this is with fairly large amounts of data, right?
Yeah. I mean, this is one sample tile, so.
Oh, okay, just one sample.
It's not the global.
Maybe you should do it across a few more tiles, so just that you don't. It looks weird to see that.
Yeah, it's probably something related to like if the tile has a lot of empty ground or something like that, would look different.
Yeah, just do it across.
Yeah.
Okay.
So overall, the calibration looks really good empirically. And yeah, I mean, people should be checking this on like how well the model actually calibrates your uncertainty that you're trying to learn. Okay. And yeah, that's pretty much all the results I have, and I will discuss a couple of thoughts I have on what the extension is. So temporal dynamics, because I was basically only training and testing on 2022, and people do care about the temporal change of biomass, of course, because deforestation is a temporal dynamic and not a spatial exclusive one. So what I've actually been doing some work on this, and it also works. So I'll just give you the teaser that it works, and possibly in a future seminar I'll also talk about that. And then for active learning. So if you have good uncertainty, what does this give you, except for the fact that you have good uncertainty now? So my argument is that conceptually, if you could have a confident guess on what the uncertainty is for any given point, you could use this as a little model to tell you if you're doing field work or something. You can train a model to guide you on where you should be sampling to maximize your information gain from doing sample work, because people have finite budget or time when they're doing field work, right? And then usually they do like stratified random sampling or something along those lines, but that's not probably ideal as to information gain. But if you have a model that tells you where it thinks you could maximize your information gain by sampling, then you can make your sampling either cheaper or more informative, which is a very cool property that fell out of this. And yeah, the summary is that if you're using standard machine learning models or metrics like Random Forest and XGBoost, you could be checking uncertainty, almost certainly that you should if you're doing any sort of mapping that you do want the uncertainty about. But you should think very hard about what the metrics that you're using are and what it means mathematically, because this matters a lot as to whether it actually reflects anything in reality. And the ways that you could do that, I have been spending the past half hour talking about it, so pick one of them. And yeah, so you should care about this. It's possible to do, and then it's possible to do well. So even if you're not doing like a neural process, you could be using something like a quantile XGBoost, which actually performs quite well, even with the trade-offs. But you should be checking the calibration as to what you're actually getting from learning uncertainty. And if it's doing well, then you could trust it. If it's not doing well, then you should caveat that with saying that the metrics are not reflective of reality. And if you're doing random forest with ensemble variance, don't do that. Yeah, that's everything, and I'll be taking questions.
Thank you. Okay, any more questions? Jason?
So I think it's really interesting work, really cool. But essentially what you're doing is training a model to predict another model, which is one reason I think you should be slightly careful. So GEDI is calibrated.
Yeah.
Right, and it's a biomass model, which is based on eventually field plot data.
Yeah.
But it seems like your approach could incorporate field plot data.
Yeah, good. Like, yeah, this generalizes to any like sparse ground data, and I'm just using GEDI because it has a good like sample.
Points,
Yeah.
And it's not like biased in the same way some would be, might be biased in a different way. And it might be interesting to consider how you deal with some bias.
Yeah, that's true.
But yeah, I would suggest maybe because the GEDI calibration data is available, or at least parts of it are. So I think to just like check how well the model is doing, you might want to.
Yeah, like this, the implicit assumption here is that the GEDI L4A shots are reflective of the ground truth, which they probably are not perfect, but they're a reasonable proxy of. And this is like going from that to a good map, what you should be doing. Well, like you could take this and do any sort of learn it on any sort of like true data that you have good confidence about, and it will still work. And on related note, neural processes were originally conceptualized for few shot learning, so it could work very well even with much less samples because of what it was originally made to do.
By the way, we did share this with Amelia.
Yeah.
On the GEDI team, so she had quite a few comments on that.
I just think so. If you're talking about the kind of partitioning and philosophies of uncertainty, that would be a logical next step, right?
Yeah.
Kind of see like where the gap actually exists.
Yeah.
Because you said, was it Hokkaido was doing quite poorly?
Yeah.
And typically GEDI does quite badly in mountainous regions. So there's a lot of uncertainty on that GEDI itself.
Yeah, the GEDI source quality is not the. So sometimes it has very weird stuff like hitting a cloud or hitting a cliff, and then it will pop out like a 3,000 measure that's totally unrealistic. Yeah, so I just have to filter those out into a reasonable range.
That might explain some of the variation between regions.
Yeah, question.
I would add one question. So let's say you're training the random forest. So essentially just input, because each data point is corresponding to a 3x3 patch of tensor embedding.
Yeah.
So what you do is like you feed this 3x3 patch into the random forest, and you map it to the GEDI point.
Yeah.
Yeah. And also when you feed this into the random forest, are you doing any other like curve processing? You just like feed it like a 9 points, or are you using a like very small CNN on top of it?
No. So for random forest, it's just plotted, and then for the MP, it has a small encoder, CNN encoder.
Oh, I see. Okay. And also, like if my understanding is right, so let's say if you train your model, let's say ANP or whatever model it is, on a lot of GEDI points, does that mean you can actually create a global GEDI map? Like
With uncertainty.
Yes, with uncertainty.
Yeah.
And do you think like how difficult it is to do that? Like
very easy if you have compute. I don't have compute.
Well, we will get compute soon. But I mean, but this is exactly right. I mean, we could create for all of the world biomass map.
Is there any like product already, like kind of product like this one?
Kind of, yeah. So nothing at the 10-meter scale, but there's a 100-meter scale one. But so the prior work on this is mostly people try to use deterministic models like regressions because they trust it very much and they could interpret.
But I would say there are two separate things here. One is just what you've done, which is valid regardless of how shitty GEDI might be, which is, hey, how these are the advantages of this kind of approach that gives you uncertainty, that gives you all these things. It's applicable to any kind of map, any kind of data sampling, and that stands on its own. And then the second one is if you want to make a good biomass map, which first of all, there's like a lot of people trying to do this. And then you also don't want to just use GEDI, probably. You want to ideally calibrate it with ALS data. Then you're getting into the whole, it's a more, I mean, you could just have like a GEDI global map. And I think there's a couple already published to some extent or like trying that. And then you're arguing just that this one would have uncertainty.
Yeah, and I think the point is very well taken. I mean, GEDI is it's good for getting structural complexity measures and point measures. GEDI biomass is anyway a derived product. I think James has already clarified that point. And I think if our goal were to say we want to create the best possible biomass map, then we wouldn't go with GEDI. That doesn't make any sense. We would be using the plot network or other ground truth network and using this to interpolate it. So the point that Robin is trying to do is more of how do you do proper interpolation of sparse ecological data. And we didn't have access to sparse ecological data. So GEDI is just a proxy for it. But the point you're making is also good, which is can we create a biomass map at 10-meter scale for the world? And that's a very useful thing to do. But then the ground truthing for that would be coming from from plot networks, and similar to the habitat mass stuff that David is doing. I think we need access to all these, and then that's a different
LiDAR.
game altogether.
Yeah, you want LiDAR.
Yeah, I mean, you want to get Tommaso's
Exactly.
database of LiDAR, ALS. Isn't there? Tommaso's got a database now, right?
Tommaso's collected a lot.
Yeah. So there's a whole ALS, and then you can get sub-meter. Sub-meter is too small. I think the consensus is 100-meter scale is what you want, something like that.
Yeah, you don't want to be going too fine. Because people would like developing these like super resolution.
Yeah,
but it makes
no sense at all. So let's say 100-meter scale, then you would use 100 10 by 10 patch tessera plus ground truth. Then do the ANP and then create an interpolation. That could be a very nice master's thesis, for example, to do this. Take Tommaso's data, take Tessera, take Robin's work, and create a biomass map at 100-meter scale globally. Yeah, I mean, the problem is going to be temporal variability. That's the next thing that needs to be solved, which Robin has been looking at. In other words, some of the plots would have been measured in, let's say, 2014, so in 2017, so in 2019, so maybe remeasured a couple of times. How do you do that kind of spatial and temporal interpolation? Because the biomass is going to change over time, right? It's going to increase or potentially degrade. So the spatial temporal interpolation, along with ANPs, is actually teaser, but that's very important.
I think the temporal domain is very interesting. Yeah, I've done work before on biomass forecasting.
Okay.
And so being able to describe a distribution rather than a sort of set value is very useful because you might have deforestation, so you might have like a long tail of kind of negative values. Generally like a lot of positive values.
Yeah, but here's the thing that the temporal stuff is usually not doing, and I don't know about your work, but let's say I have a point A and I know the biomass at this point in time, and I know the biomass of a point 20 kilometers away 2 years later. What can I say about this point 2 years later? In other words, I want to use both the spatial and the temporal context to leverage those. So not only I want to use nearby and space and time points to get the context. So using the additional context is going to help you a lot. And existing work, I don't think uses the spatial temporal context. It's just going to do time series forecasts of the known point. That's why they want to do repeat LiDAR scans of the same location. Here you can use the data from a nearby location. And also what you can do is for locations which have places where you don't have forest plots, you can say, okay, you can fall back on GEDI. And so you can say, you can sort of have this layered approach where you say, will you use forest plots where you have it? When you don't have it, they'll use a broader model, which could be something else. And it would still be giving me some context.
I think if you could do that, it would be very, very popular.
I know, so you got to find a master student who can pick it up. But or Robin might do it. He has lots of spare time right now.
I don't really want to get into like data fusion hell of having 100 data sets I have to get together to work.
Robin, these neural processes, like what kind of tasks are they good for? Like, is it regression tasks? Also, what about classification tasks? What about, Yeah, just.
You could do both because it's like it outputs it learns the distribution, right? So you could, as long as you could specify the functional form of it. If you specify a binomial one, you can learn classification.
Could be very helpful for our because we've got such inconsistent state terms.
Yeah.
And how much longer does it take to train?
Oh, pretty much the same.
Okay.
Yeah.
Than a random forest?
For XGBoost, yeah, random forest is weird because random forest scaling is kind of exponential. Yeah. But it's like I trained like 1 million parameter model is very quick. And it works well. Those like neural processes are in general not very big.
Okay, any other questions? All right, otherwise we're ending exactly on time. Let's thank Robin again. Okay, I think that brings us to the end of. I tried